Good morning again, and we're going to get started continuing our study of MO theory today, where we're going to make a big jump forward today into looking at heteronuclear species. But I want to refresh where we sort of ended last class, looking at the MO diagrams of a homonuclear diatomic, so meaning both nuclei are the same. So we have a bunch of pictures like this in our textbook, okay? And I want to show you there's a lot going on. There's three things going on in this figure that we're looking at here in the textbook. The middle is what we're most used to drawing and creating for an MO diagram, showing the pre-bonding, as it would be, atomic orbitals on the outside, and then how those come together to form bonding MOs in the middle. And I wanted to bring this up to show that energetically speaking, when the two atoms are the same, what we see is that equal splitting, essentially, of the bonding down, lowering energy, and antibonding up in energy. All right? So everything looks pretty symmetric about the starting points, right, for the bonding. These things on the sides are images generated of what these MOs look like. You just asked me a question about the shapes and how they interact, right? So you know what an s orbital looks like. It's spherical in shape, and a p orbital, right? So what do the molecular orbitals look like? And so these can be calculated because they are just, again, the result of a wave function, an equation that describes them, all right? They get more complex, but so these are, computational renderings of what those equations would look like, squared. So you're looking at really the probability density of where the electron is in space, okay, to give you an idea of what that is. And then this is a sort of a different version, a simplified version of showing that, all right, with a little bit less nuance of the shading and everything. Just a little more simplified version of really what's going on in these. And they spread it out. So this would be not even seeing anything else, but we could tell that anything that looks like this would be a bonding molecular orbital. The two dots are representing our nuclei, right? And the shape is showing us the region in which the electron is likely to be contained. So we see plenty of space included between those two nuclei where the electrons can be, and that's what's going to hold the molecule together, is the mutual attraction of the two nuclei to electrons that are in between them. But this orbital up here, there's no spot between them where electrons are likely to be, right? The electrons are housed in these two little smaller regions, each around the nuclei, which, as we said last class, don't help hold the nuclei together. There's no mutual attraction. They're each individually attracted, you could say, from this picture, to the electrons around them. So that's why it's an antibonding orbital, okay? Again, bonding, antibonding, bonding, right? Again, the dots would be right here, but there's space between them. These are bonding. They're a little bit different, though, because it's a pi, right? So it's not quite as strong, but there are plenty of regions of mutual attraction. And then you have the clear node here of antibonding. And then this one's an antibonding because there is a node right between the two there, okay? So that's what these figures are. Again, this is the case of the two nuclei are the same. Let me forward to a heteronuclear case. Like carbon monoxide is the classic, simplest one that we look at, although it's really not that simple. All right, so here is the carbon monoxide case. And I may need to zoom in a little bit and then pull up, okay? So what's going on in carbon monoxide is that the atomic orbitals now are no longer equal in energy, right? They're now starting at different energies, and that's what this is representing. There's a scale of energy for us here, okay? So we see that we've got carbon here on the left, oxygen on the right. The symmetries should suggest that the s orbitals are a good match for each other. As we just had drawn up here, right? I mean, the carbon 2s looks like the oxygen 2s. So there's a match in symmetry that should allow those two orbitals to interact with one another. But the oxygen is much lower in energy because the oxygen atom is smaller, and so its s2s orbital is actually pulled in closer to the nucleus due to its increased effective nuclear charge, something we learned how to calculate a chapter or two ago, right? So when we go to mix these two, the mixing is no longer equal, all right? And it's kind of like a rich person going out to lunch with a poor person, all right? You know, in an ideal world, the rich person would understand their place and would contribute more towards the bill for lunch, okay, and ask less of the poor person there, all right? So when our orbitals mix, it's not about money, but it's about energy, okay? They're not equal in their energy, so the combinations that result reflect greater contribution from one atom or the other. Now we still get a bonding, a lowering set, and an antibonding, a raised set. But the outcome is that just a second ago, this was, remember, perfectly symmetric. Okay, the version of this for the homonuclear diatomic. But now look how lopsided it is. Okay. It's got similar idea, two little sides to it, two lobes to it, but one of them is much larger, and it's larger on the oxygen side of the molecule, meaning this molecular orbital is concentrated more on the oxygen atom. Okay, it doesn't belong to the oxygen, it really belongs to the molecule, but truth be told, it looks a lot more like the oxygen. Okay, and that's where its proximity. Whereas the antibonding orbital that forms from the two s orbitals that are bonding, right, is concentrated more on the carbon side because it is closer in energy to carbon's original thing. Okay. Now again, all of these come from calculations, and this is stuff that you start to do in PChem, and if you learn how to use molecular modeling software, like you will here, okay? Don't think of it as a punishment. You guys are given a step ahead of most schools in terms of the amount of modeling experience that you'll get, all right? We're hearing more and more. Some of the faculty just went down to a big company the other day, down to BD, down in Maryland, and met with them about starting up some internships for our chem students. And they wanted to know, what are the computational skills like? The writing of software code and the performing of calculations. All right? So you see, it's going to be a demand in the job market. And you're going to learn how to do it. It's a little bit of a learning curve and a pain to get started, all right, for those of you who haven't had PChem yet. But, I mean, you guys are going to have, Dr. Forsman is one of the experts in this field, okay, and the company that he works with, Gaussian, all right, at calculating these things here and visualizing them and helping you understand that, okay. So the pictures can say a lot. They just show you where the orbital is concentrated and on which atom it has. Okay, so if we scroll up and look at the sets that come from the P's, we see some similar stuff here. And zoom out a little bit so I can see a little bit more of the P set. Okay. All right. So again, when the P's mix now, we get a variety of things. These look a lot like the pi orbitals that we saw for homonuclears, okay? But again, they're a little larger on one side than they are on the other, okay? Here is the sigma that forms, right? You can see it's a sigma, how it's, again, still symmetric about a C2 axis going this way. So if you rotate this molecule, this orbital, sorry, there's no change to that shading or that shape, and that's why that's a sigma, okay? And again, these are concentrated more on the oxygen. This starts to shift more towards the carbon is what this is telling us. And these all over here shift more towards the carbon as well. These being the carbon 2p orbitals that we have here. Okay. Now, it's pretty complex stuff to figure out the weightings, what would be the coefficient of each of the wave functions, right? Each of the MOs is a combination, right? The wave function in the MO is some combination of the wave function of, of the first atom plus the wave function of the second atom, all right? And in a quantum mechanics class, you would do the nitty-gritty work of trying to figure out these coefficients and these weightings. Last class just showed you that, like I just said, they're equal for homonuclears. These would now be unequal, right? That's like the analogy of the rich person would have a bigger coefficient. They would pay for more of the lunch than a poor person would, okay? And then so that weights the overall molecular orbital to look more like that atom's atomic orbital, in other words. Okay? We're not going to get into that degree of specificity in this course. That's not what we're supposed to do in this class. But we do need to understand when we see these pictures kind of what they're relating to us. Right? What we're going to get into is an approach, a really clever approach that lets us predict which orbitals from each atom are the best match for one another. Okay, sort of a qualitative way of coming to an understanding of, how far apart is too far apart for them to interact. That's one of the criteria that we talked about for MOs to form. Okay. And what sort of shapes or symmetries are allowed to interact with one another. Okay, so I think that's kind of what I wanted to say as a stage setter for this. Where's my textbook for the day? Okay, so there's this figure in the book that we looked at the other day. That is all of these numbers of the energy levels. Okay, I'm going to bring it back up again. Holy cow, it's far away. There we go. Okay. So again, this table in your textbook, 5.2, is going to come in very handy. I'm going to go through a set of rules in a minute here, but I just want you to remember this table that exists. And there's an even larger version of it in the appendix in our textbook that has even more of the orbitals in it. This is just focusing on the S and the P. I think that table in the appendix has some of the D's in it as well, okay, which you may occasionally need, right? So again, these are the energies of, if I pick boron's 2s and 2p orbitals, okay? And energy is important for considering that weighting that we just talked about. All right? In a homonuclear, they would be identical energies, right? But in a heteronuclear, they're going to be a certain distance apart in terms of energy. And I'm going to give you the criteria in a second that say what's too far apart for this. Okay. All right. Okay. Any just questions so far on this idea? Of the fact that we have these heteronuclears and they're different from each other. Okay. All right, let me turn the projector off and get to the board then, or at least mute it now. Okay. So what we're getting into is what's called the group orbital approach. The group orbital approach is going to group together the atomic orbitals of the exterior atoms that are attempting to bond to the central atom of a molecule, okay, and use group theory, like we just learned in the last chapter, okay, to determine their symmetry as a group and how it matches or doesn't match with the shapes of the orbitals of the central atom. Okay? When you have match, you can form bonding and antibonding molecular orbitals, just like question 2 on the homework that you just handed in and asked me about, right? But, you know, for like 5 different things trying to bond to an atom, how do you decide, you know, what the collective shape is? That's the power of the group, okay, and the group theory approach. So there's a sort of a visual way to do this, okay, which we'll run through very quickly. But then there's sort of the more mathematical or it's not super mathematical, but it's the group theory way. Okay, so if we consider, this is a really weird molecule to consider. Consider FHF minus 1 as a charge, right? All right. The hydrogen 1s orbital is no problem to understand, right? It is just a shape like that. It's a circle like that. But each fluorine has both a 2s, and then it has the 2px, 2py, and 2pz orbitals. Okay? So the 2s would look like this. Now I'm going to establish my z-axis as right down through the molecule that way. Okay? Right? So my 2pz's would be oriented like that. Okay? We'll take, doesn't matter what's 2py and what's 2px, one's going to be up and down, and then one is going to be, you know, coming out of the board at us like that. Okay? Now we have 2 fluorines. Okay? So what we want to do in this group orbital approach is consider the fluorine orbitals and how they might interact with the hydrogen 1s orbital. Because if any bonding is going to occur, that's how it's literally going to happen. The hydrogen 1s has to be able to interact with these fluorines. Okay? So now there are 2 fluorines. So let's establish sort of a line. What I'm going to do is I'm going to be putting the hydrogen in the middle and then 2 fluorines on the outside. So let's consider the 2s orbitals, right? They could be of the same sign, or they could be of opposite signs, right? And the 2s orbitals, they each have their own wave function, their own possibility for what their sign is, okay? So they could be in phase or they could be out of phase, right? So if we stick the hydrogen 1s orbital in there, so this is our H1s, and then these are the 2 on the outsides are our 2 fluorines. Is this potentially a good symmetry match to allow bonding to form? What do you think? Can they overlap? Can the orbitals overlap? The shapes like we just did on the homework and stuff? Okay. Yes. So this is a good match. All right. So let's say this is good. Okay. What about this right here? Stick the hydrogen 1s in there. Are we going to get bonding or not? Can we get overlap or not? No, why not?
Because one side's shaded, one side's not.
Right. This is just like the argument that I showed before class, right? That about the one would cancel. This would be good overlap, same sign, but this would cancel it. All right. So there's going to be no interaction here. Okay. Now let's look at the 2pz. Okay. So here's my 1s in the middle again. Now we're going to draw our 2pz's. Oops. Okay. Now our 2pz's can be in the same phase with each other, or they can be out of phase, just like the 2 s's were earlier, right? They can be the same, or they can be flipped from one another. Okay. So when we consider then the 1s between the 2pz's, is this going to result in bonding / antibonding orbitals? No? Why not? The one on the left cancels the one on the right again, right? Opposite signs, so that's bad, that's good there. Right? So no interaction here. What about over here? Now, I drew the hydrogen out of phase, right? So I could draw it to be the same sign, right? Notice that changing this here wouldn't change the outcome, right? So changing the sign, you'd still get, now the favorable's here and the unfavorable's here. All right, so it really doesn't matter, okay? That's just determining bonding / antibonding, right? But this is now favorable overlap, okay? And so this is a good match for symmetry and can result in the formation of a bonding or antibonding if the signs flip from one another. Okay? Now, how about our 2px? Our 2px would be oriented like this, and our hydrogen would go through that. Again, we have to draw the x's in phase, or we have to draw the x's out of phase from one another. Is either of these going to allow for a potential bonding and antibonding case? No, right? In each case, you're going to get the half cancellation, and here half. So it doesn't matter. So again, this is no, all right? And then if we go to the PZ or PY, it's the hardest one to draw, coming out of the board like this, right? But the same thing, it would be no, whether they're in phase or whether they're out of phase. I drew that one too far away. Okay, so again, there's no interaction for either the PX or the PY. Okay. So the two fluorine atoms combine to make 8 possible groups of orbitals that can interact with the hydrogen. 1, 2, 3, 4, 5, 6, 7, 8. See it? Okay. Of the 8 groups of fluorine orbitals, only the 2s in phase and 2pz out of phase, right, are potential symmetry matches for the hydrogen 1s, for the 1s orbital. Okay? So we've made our life actually a lot easier. We've now narrowed the field for how this bonding occurs, for what orbitals come together to do this bonding, down to 2 possible groups. Okay? So now, from that table, from table 5.2, the energy of the hydrogen 1s orbital is negative 13.61 electron volts. The energy of the fluorine 2s orbital is negative 40.17 electron volts. And the energy of the fluorine 2p orbital is negative 18.65 electron volts. Okay, so that big table that I showed just a minute ago, that's where these 3 numbers came from. Okay, just got to dig in and find them. Okay. So let's sort of visualize this pictorially, right? Here's energy, becoming more positive, right? So if we put our hydrogen here, our fluorine 2p's are a little lower than that. And our fluorine 2s is way down here. Way far away. Okay? Symmetry tells us that both of these sets, the 2s of fluorine or the 2pz of fluorine, are the right shape. But now energy is telling us the 2p is the better match. Okay, because it's not just the shape. These things literally have to be close enough in energy. All right. I mean, this is, something way, way far away, right? Like a Bill Gates would never interact, with some really, really, really poor person just on the street. They're just not going to get a chance to interact and meet. Okay, even if they might share a common love of Microsoft products or whatever. Okay, they're just too far away in the circles. Okay, but this set here is a little bit closer. Okay, all right. So this is where the interaction is going to occur. All right. Now, what would that be? There would be. So this one would just come straight in. Would be a non-bonding orbital. But then the one would mix with one of these and with one of those. You'd have to form a bonding and an antibonding. And then the other two would essentially be dumped in. Because you can only mix one, right? If you're only donating one from here, it can only technically combine with one of the P. Well, actually, these are all of the P's. So it's the PZ that goes down here. The PX and the PY, by the way, did nothing, right? And so they go in right there. Okay? Okay. So this is roughly speaking how you can generate an MO diagram and figure out which orbitals do and don't conspire. Okay? So, the real question that you should be thinking is, what is too far apart? Which energies, are too far apart? Okay? And I'm trying to make sure I see where it is in the book, because it should tell us. I thought it gave us I believe it's any, if we ignore interactions when the difference in the orbital energies, when the delta E is greater than about 15 electron volts. Okay? It's just too far apart to overcome. That's what I should have it underlined in here, but it might be in the summary section that I'm looking at. Okay. Now, this isn't too bad, I don't think, right, drawing out all these pictures, but that's, a pretty simple structure. If you had 3 atoms on the outside, right, and then, or 4 atoms on the outside, and they're not all in a straight line, you can imagine that the pictures are going to start to get a little more complicated and complex. And that's where the group theory work can come in and sort of step in and take the place of what we've done here. Okay? And so this can be sort of recast, so to speak, into the language of group theory. Okay? So the we can the sort of the process here for predicting which exterior atom or which exterior atomic orbitals combine with the interior atomic orbitals. This is described in much more detail, by the way, on pages 143 and an example through page about 144 for the example. Okay? But I'm going to give you a quick summary of it. Okay, so the first thing that you do is determine the point group of the molecule. Okay. And some of the point groups are less friendly than others, so the suggestion is made that if it is d infinity h, use d2h instead, because there are fewer operations, but it's going to lead to the same outcome. A d infinity h would be a molecule that has it's like a pencil. It's a straight line, okay? So it's going to have that infinite axis of rotation, and so you could ignore that. One other substitution is if it's c infinity v, use c2v instead. Okay. The second step is to assign your coordinates. Okay. Coordinate assignments. Okay. What you want to do is use the Cn axis as z. Okay, so if you had a C2, if you had a C3, a C4, just like we really did last chapter, with symmetry stuff, you want to retain that as your z-axis. Okay. Usually, here's an interesting little thing, have the y-axis of the exterior atoms. Okay. By the way, this is also done on each atom. Okay? All right. Although the z-axis is the same for all. But what you can do for the... wait, I might be ahead of myself, actually. Nope, this is right. Have the y-axis of the exterior atoms point towards the center, or the central atom. So the y-axis on one atom isn't necessarily exactly the same as the y-axis on another. All right, but this is okay because you're considering how it's going to transform from the central atom, so it won't be that big a deal. Okay. Okay. Third is you're going to construct a reducible representation of the exterior atom, or exterior atomic orbitals, okay, in groups, I should say. So in groups, your groups would be your S, your PZ, your PY, and your PX. When you do this, same rules apply that we really learned before. If an orbital moves, it adds 0 to the gamma, to the reducible representation. If an orbital is unchanged, it adds 1 gamma. And then if an orbital sign changes, it adds -1 to gamma. Okay? So sort of like we did with our vectors back in chapter 4, right? We took our 3, but now you're doing it for an orbital rather than thinking about three vectors and your fingers in which direction they point. Okay? We're doing an example with all this, but I'm just laying out the process first. So once you develop a reducible representation, guess what you do next? you reduce it, okay, because it is reducible. So step 4 is to reduce each representation, okay, into its irreducible representations. Okay. All right. What you're doing in this step here, okay, the book explains this here, is this finds or identifies the symmetries of the group of atomic orbitals. So this really takes the place of the pictures that we had to draw a minute ago, right? And all those different pictures, all right? This step identifies, oh, there's an A1 symmetry. There's an all-symmetric symmetry present. Or there's an E symmetry present. Those labels that we saw in the character tables, right? Which all identify some symmetries, okay? These are sometimes called the SALCs, the symmetry adapted linear combinations. We won't use that too much, okay? Next, use the character table to identify the symmetries of the interior atoms, okay, of the interior atoms orbitals. Okay, so these are going to be, I'll show you this, but these are given in the right-hand columns. Remember the columns that we used for IR and Raman identification last chapter? Now, they also tell us the symmetry of the orbitals of the atom. Okay? So, you know, it's just going to be looking in the same place that we looked before. All right? Okay. And then, lastly, now you match, okay, match orbitals of like symmetry between the group of exterior orbitals and the interior orbitals. Okay? And then you also consider, as a last step, you consider energy matches as well. Okay? So the orbitals that match, you know, this is where you'd really be making the picture that we have over here on the right board for our FHF molecule, right? So the orbitals that match will make the MOs. Okay? So what this whole process is going to do is it's going to reduce the complexity. It's going to take dozens, in some larger molecules, dozens of potential interactions that you might have to consider of this orbital on one atom with a whole bunch of different orbitals on this atom. And it's more efficiently going to cut away what are not possible matches for you and narrow it down to, oh yeah, here are the two groups that you need to consider. Okay? It's the power of the symmetry that's contained in group theory. Okay. Okay, any questions on the writing? Obviously, it's out of context. I can understand right now if there's plenty of questions on the concept or anything like that. And we're going to go through an example, all right? But just, you know, Anything need repeated or whatever at this point as we go through it? Okay, so let's look at carbon dioxide as an example. Track it just like it does in the book. Okay? Carbon dioxide is actually in the D infinity H point group, so we're going to use the D2H group instead. Okay, so step one, identify the point group. Okay, all right. Our molecule, our CO2 molecule, so this is going to become our Z-axis, right down through there. Okay, that's our CN axis. And then it won't matter what's X and what's Y. Okay, X and Y are really identical. They're going to be redundant. Just to be consistent with the book, they're using X as the vertical and using Y as the axis that comes out. Okay. What that would mean is, your PXs are going to look like that, and your PYs are going to look like that. Okay, coming out of the board. And then your PZ obviously would be pointing towards the carbons. Okay, so we need to establish those coordinates. So now what we want to do is look at our D2H point group. Okay. The operations that are present in the D2H point group are E, C2, that is the Z-axis, a C2 that is the Y-axis, a C2 that is the X-axis, center of inversion, a sigma plane X, Y, a sigma plane X, Z, and a sigma plane Y, Z. Okay. So now imagine a picture of your two 2s orbitals of oxygen. Just like we did earlier for the fluorines, right? Okay, we're going to divide and conquer. We're going to look at the oxygen 2s's. How would this picture, how do these two orbitals transform under each of these symmetry operations now? This is step 3. Develop the reducible representation. Okay? So, for E, neither of them would move, and neither sign would change, right? So they're fine. For C2Z, the Z-axis, neither of them moves, right? It's the axis right through the molecule there. For C2Y, through the Y-axis here, here's your X and here's your Y-axis. For C2Y, they would move. So the character is 0. For C2X, they would move as well. Okay? For center of inversion, they would move. For the XY plane, that would be a plane coming out of the board like this, they also move. So that's 0. For the XZ plane, that is the board. So do they move? No, then they stay in the same place. And for the YZ plane, that's this coming out of the board, again, they don't move. Okay? So we've developed the reducible representation just for these two 2s orbitals. Okay? All right. Now you'd repeat this for your 2pz, your 2py, or your 2px, or 2py. It doesn't matter what orbital you do it in. Okay? So for the 2pz's, now you need to put, it doesn't matter what colorations you put, you'd get the same answer, but you need to put some, obviously change of sign in there on those. Okay? Because the two lobes of any p orbital are opposite in sign. Okay? So how is this going to behave when we conduct all these operations? 2, 2, 0, 0, 0, 0, 2, 2. It's identical to the 2s, actually. has the same symmetry as the 2s set. Okay. Now how about our 2px? Our 2px is how's this going to behave? 2. Now when we do the 2p, now when we do the C2, right, here, they're going to stay in the same spot, but their signs are going to change. So it's going to become minus 2 upon the C2z. It's still going to be 0 and 0 for the other two C2 operations because that's centered on the carbon, so they're both moving. Okay? Center of inversion, they're moving, so it's 0. XZ, or XY, sorry, again, they're moving. See, these are all going to be zeros because the orbitals move, okay, on the oxygens. Now, XZ, again, the plane of the board, okay, so that's really flipping front to back. They're the same. But YZ now, coming out of the board, right, is going to flip their signs again. So it's going to be negative 2. Okay. All right. One more set, the 2p, that was 2px, this should be 2py that we have left. So the 2py's will be coming, I'm just going to draw them on here. All right, so there's the 2px, and now here's our 2py. Okay? Okay. Similar behavior, 2 minus 2, all right? 0, 0, 0, 0. But now on XZ, okay, which is the front to back flipping, the 2py's change sign. And on YZ, they're in that plane, so they don't change sign. So you see how these switch signs over here. Okay. Any questions on developing these reducible representations? It's not quite a speak now or forever hold your peace, but this is a good opportunity to speak if you're still not getting it. Okay? And lets me have a cup of coffee. So, all right. So, no. Okay, next. Reduce. Okay, good. I can keep this board up. So step 4, reduce the representations. Okay. This is why we had to learn how to do this last chapter. And hopefully why you got efficient and good at doing it. As you do it more and more, and you look at the entire character table, hopefully you start to get a little faster at picking out what you don't have to test every single irreducible representation, in other words. Okay? You could start to, by use process of elimination, to figure out, which ones are zeros very, very quickly. And so, if we look at the D2H point group, again to write it out here, okay, our E, our C2Z, our C2Y is listed next, our C2X is listed next, our center of inversion, our sigma XY, our sigma XZ, and our sigma YZ listed last. Okay. Again, we're looking for things that are going to add to 2, right? So we're going to want things that have 1s, which all of these things do in this point group. But look at all these zeros we want, right? So you would want to look for 2 irreducible representations that have opposite signs for all of these operations, so that when you add those 2 representations together, you get zeros. Okay? And, in short order, the A1, or the AG, as it's called in this case, because there is a center of inversion, which would be all 1s. And then the B1U has 1, 1, minus 1, minus 1, minus 1, minus 1, 1, 1. Okay. So even without doing the reducing, right, can you see those add to 2, 2, 0, 0, 0, 0, 2, 2. Okay? So the gamma for 2s equals AG plus B1U. But hey, the 2PZ had the exact same symmetry, right? Or the exact same reducible representation. So we've got two for the price of 1 there. Okay? But we can confirm this. We can do the reduction if we want to, all right? To figure out the n of AG in gamma 2s. All right, well, what's the sum of this? 1, 2, 3, 4, 5, 6, 7, 8. That's the order. So it's 1/8 of, you take this times that. So you'd have 1 times 1 times 2, plus 1 times 1 times 2, plus a bunch of zeros, 4 zeros, plus, in the end, you'd have 1 times 1 times 2, and 1 times 1 times 2, 2, 4, 6, 8, divided by 8 is not 8, it's 1. So you have 1 AG in that representation. Okay? And you can confirm it would look the exact same because of the signs are the same on the outside ones for that. Okay? All right? So again, you can use the reducing process. Okay? If we look at the 2px and the 2py, okay, they might get a little bit harder to come up with there, but they end up giving us the 2px ends up giving us, I think, a it's not listed here yet. I think it's a B3U is contained in it there. So let's see if we can figure it out real quick. Let me look back here at my numbers, and I've got the full character table here. So we want -2. So we want there. No. What? 2 minus 2. So we're probably looking at like a B2G. That's good. That's 0. That's 0. That's 0. That's 0. That's 2. And that's -2. So it's B2G plus B3U, which can be confirmed. That's actually what the book says. The book says confirm these reductions. So we could do those out. And the gamma for 2py, if I could try to do that in my head, let's see, they're going to flip. I think they might just flip. It's 2 minus 2 still. Yep, so 2 minus 2, 0, 0, 0, 0, then -2 and 2. Yep, so it becomes B3G plus B2U. We just flip where the 2 and the 3 were. Okay. So in doing the reducing, don't want to get us off track, what we've decided now is that the 2s orbitals of our outside oxygens have a symmetry described by AG plus B1U. These labels that describe how a molecule transforms under all these operations. The 2pZs share that same symmetry. The 2px's have the A2G plus B2G plus B3U, and the 2pZy, have the last one there that we flipped. Hard to see at that angle. B3G plus B2Us. Okay. Now, step 5. All right. Use the character table to determine the symmetries of the atomic orbitals of the middle atom, the interior atom. All right, so if we have the character table here, again, I'm going to have to draw this out. The D2H, E, C2Z, C2Y, C2X, okay. Next was the center of inversion I, and then the sigma X, Y, sigma X, Z, sigma Y, Z. Right. Okay. Forget about all the labels and everything for right now. I'm going to look at the far right-hand side. Way down in the B1U, B2U, and B3U labels, all the way over here on the right side, the next column, to the right of all the characters, next to B1U, it lists the letter Z. Next to B2U, it lists the letter Y. And next to B3U, it lists the letter X. What this means is these are the symmetries of the p orbitals. Of any interior atom in this geometry. In this point group, right? It's specific to the shape of your molecule. So it's not like in every molecule, this is where the Z is going to be. It's unique to each one, but it's identified for us, okay? So what the table is telling us is that the carbon 2pZ orbital has B1U symmetry. And the carbon 2pY has B2U symmetry. The carbon 2pX has B3U symmetry. It's as easy as looking at the table, finding the letters X, Y, and Z. Where is the carbon 2S? Any guesses? What's the symmetry of an s orbital? If you had to describe it across all the operations, how's it going to transform an s orbital? It's always the same, right? It's all ones. Which representation is always all ones? A1 or AG or whatever. The first one listed in every table, guys. You've got to pay attention to stuff like this. All right? That's all it is paying attention. Waking up and paying attention. In every single one of these tables, the first one is the all symmetric. So in this case, it's called AG. And again, the G is here because we have a center of inversion. So Gerard and Ungerard, right? So it's not going to be listed, but the s orbital is always all symmetric. Okay? So we could say that the carbon 2s has AG symmetry. Okay? So again, it won't be listed, but that's what it is. Okay? Now there are, not in the case of carbon, but in the case of larger atoms, particularly transition metals, all right, in the third period and below, there are d orbitals. The d orbitals would be listed in the next column over. Right? We used those for the Raman spectroscopy stuff last chapter, but we don't need to worry about them right now. But sometimes they are useful for forming the bonds in molecules. All right. I think anything that goes beyond 4 bonds is going to need those d orbitals. Yeah.
So in the character table, when doing problems like this, if like we see one without like a zx or y in the right hand column, should we just assume that's symmetry with the 2s?
No, the z, x, and y will always be listed.
But if it's, because I know like in some character tables there's nothing listed, so would that character be the symmetry?
Oh, okay, so there's no, I see, you don't see anything in these other columns or whatever. I guess that means that the orbitals are not described by any of these symmetries here. But maybe you were looking at incomplete versions. I'm looking through our book real quickly, and I can always find the X, the Y, and the Z here. So maybe they just weren't included in the versions that you were looking at, because that's not, maybe it wasn't part of the analysis that was going to be performed. So, okay. But you should always be able to find the X, the Y, and the Z. Okay. All right. So, where are we at? We have looked at the outside atoms. Grouped together the orbitals of the same shape, S's, Pys, Pz's, Px's, and decided what their collective symmetries are. Now we've looked at the inside atom, and we've decided what the symmetries are. Now we bring them together, right? Step 6, we match up those orbitals, okay? And that's going to predict what orbitals are going to actually be used to make the bonds in this molecule, in the case of carbon dioxide, okay? So let's get it cleaned up a little bit here. Our groups, we have, for the 2s, again, we have Ag plus B1U. For the 2pz, we also have Ag plus B1U. Right? For the 2px, we have A2G, or that's a B2G, plus B3U. And for the 2py set, we had B3G plus B2U. Now, for the carbon, our S has Ag symmetry. Our Pz has B1U symmetry. Our Px has B3U symmetry. And our Py has B2U symmetry. So the S of carbon has a match among the group of S orbitals from the oxygens. The Pz of carbon has a match among the 2pz set of the oxygens. Okay. The B3U has a match, as does the B2U. So each orbital of carbon has an orbital or orbitals. Sometimes you might have two matches. We don't see that here, okay? But that allow it to form an interaction. If you had two, then you would have to, like we did for the previous case of fluorines and hydrogens, then we'd have to consider the energies. But here, we really won't need to do that, because this is going to be the only interaction that we would have. Okay? Now, this is kind of where we're going to take this to this point. You know, what are the interactions that we would have? So we would say that the carbon 2s forms a bond, an MO, with the oxygen 2s group orbitals, the carbon 2p. So if you think about what oxygen's doing, if you draw a picture, right, of oxygen's orbital, carbon's 2s is forming one of the carbon-oxygen bonds with the oxygen 2s on one side, right? And then on the other side, there's a 2p, all right, that is forming 2pz, that's forming a bond. So there's one of your bonds. There's one of your bonds. There's your sort of your single bonds, okay? And then the 2px's are one of your pi bonds. And then the 2pz of the carbon is forming the other pi bond in the other plane. Okay. Now this is more the valence bond imagery of how this bonding works. Okay. But it's all predicted by molecular orbital theory and group theory. Okay. Now, why is there only one match? Well, because the other two px, right, on this carbon over here, or this oxygen over here, it can't bond to the carbon because it's already been taken, right? It can only bond sort of that one way, okay? And then the other 2pz off of this oxygen, again, is sort of left alone because the 2pz of carbon in the middle is bonding. We visualize it as bonding this way. And the 2pz of this oxygen, right? And then all the s's, the other s's, they're left alone. Okay, it's only one of the oxygens that needs to use its s to form one bond, a sigma bond there. Okay. All right. So again, this is the group orbital approach to this. Okay. All right. I just want to confirm that number for you here. Let's see. I'm still looking for it to tell me where the what the energy gap is. I know I've seen it before. That we ignore energy differences of a particular value. 15 is going to be fine. They're usually pretty close or really far apart. So I think we're okay to just stick with the 15 that I quoted you earlier. It may be around 10, but I don't think it'll make a difference for your homework. Okay. All right. I want to bring the projector back up and show you something that I've put together. I'll post this into Moodle for you. There it is. Okay. All right. So I have this sort of reading guide to go along with the material on this group. Oops. Why did I do that? Okay. I was hoping to scroll this down. All right. So I will post this into Moodle. This is totally an optional thing for you, right? But I can appreciate that you might be a little confused by what we've talked about this morning, all right? And you might want to see it again, hear it again. Of course, you can watch the video of class, again. But this was another way that I thought to do this in the past, where I made notes as I read the textbook and what I was thinking, and then I just typed it out for students to sort of read along with me, essentially, or paraphrasing it, and to mentally be doing. So, I understand reading is sometimes challenging in scientific text. You need to be trying to process and to actually do what is being described by a series of words in the book. And that's what this would do for you. It'll kind of make you pause and say, oh, wait, let me actually do what it just shows right here. Okay? So it's like a 5-page thing, which is why I didn't print it out and bring it to everybody. Okay? If you want a printed copy, come see me. If you don't want to use your print quota, I could do that. All right? But it just takes you through this 7 or 8 pages in the textbook where this material is laid out, and it works you through the carbon dioxide that we just did, and then I think it does the next example as well. We're going to be doing more of this next class as well. I used to try to do this all in one class. I really cut down the CO stuff that we did to give more time to this more important topic this semester. All right. So it's totally fine if you're not getting it today. That doesn't mean you don't have to work at it. You need to work at it. But we're going to see it again next class, which is until next Thursday. And you'll have this sort of reading tutorial to work you through it. Okay? So I have a homework assignment for you today. It kind of focuses on the sort of some of the underlying sort of bare bones aspects of this. There's another bond order calculation, which should be pretty straightforward. And then you're going to try to do one of these for a pretty simple molecule that has just S's on the outside. Okay, so it has just hydrogens, so you don't have to consider the P's. Okay, which is a simpler case to do. All right, so I will pass this out, and we'll see you in class a week from today. All right.